Okay, so good morning, everyone, and happy Wednesday. I hope that you have had a chance to look at the optional homework, which is due tonight. Again, it's optional, but you're strongly advised to do it for two reasons: to review the class procedures and to also just test your submission to your submissions, or how to do the submissions correctly on Gradescope, where, as usual, the thing that you have to pay attention to is that you assign the problem to the corresponding question. If you don't do that, when the grader grades, they're going to see something blank. And I know that some of you know that eventually that will mean that you will not be able to you will not receive any score for that. And of course, this is something that we all wish to avoid. In any case, in the beginning of each class, I will be writing the objectives for this particular class. And today we would like to look at what constitutes a solution of a differential equation. Or an initial value problem. So we will, you will see that we will have several times to look at initial value problem, but in most cases, we'll be looking at differential equations. You will see that it's just an extra step. And then we're going to talk about the existence of solutions. So in other words, is there anything that gives us any hope that our task of trying to solve differential equations is a meaningful one, meaning there are solutions, so we have a chance of finding those solutions. And finally, we're going to talk about Euler's method. You will see that Euler's method will be pretty much the most important part of today's lecture. And it's a wonderful method attributed to Euler, which means that takes us about 300 years in the past, that allows us to find approximations to solutions of differential equations. Okay, so why don't we get started? And let's get started by something very simple. What does it mean to say that we have a solution of a differential equation? So let me give you a differential equation. Okay, so y prime is equal to 3y. So this is a standard differential equation. Okay, you don't see what the dependent variable is, so you can choose it to be anything you like. You can choose it to be x, or in cases that we wish to imply that we're finding a quantity that depends upon time, we can actually denote it by, we can actually use t. But let's say that we would like the independent variable to be x. So we're looking for a function y of x, right? And here, without any effort to justify why this is so, I'll tell you that, for example, this function is a solution of the differential equation. You can easily test that the derivative of this function is 3 times the function itself. And I could take it a little more further, and I could tell you that this is the general solution. So this is what I would call a special solution obtained for c equal to 1. And this is the general solution for c equals 1. And this is the general solution. So the special solution is part of the general solution for c equals 1. And in some sense, I would like you to understand that this particular statement is just a generalization, extension, if you will, of what we have in the case of indefinite integrals. And this is something that I want you to keep in mind for the rest of the course, that what we're doing right now vastly generalizes the process of finding indefinite integrals. We said that when somebody is asking you to solve something like this, it's pretty much the same thing as asking you to find a solution for the following differential equation. So how were you solving this? This is your standard example of an integration by parts, right? And the solution to this would have been something like x e to the x minus e to the x plus c, right? It's the integration by parts 101, right? I mean, that's the very first example that you learn when you do integration by parts. And the thing that I want you to see here is that when you give the answer, when you find the actual solution, what you get is this arbitrary constant c, which in some sense tells you that what you're dealing with is not just one function, but it's a whole bunch of functions that depend upon this constant c. That's exactly the same situation that you will encounter in the solution of ordinary differential equations. There's a significant difference here, and the significant difference has to do with the fact that when you were doing integration, you would always be getting your constant right on the as being added to the function at hand. Well, in the case of a differential equation, the constant can literally appear anywhere. And that's why in the example that I just gave you, you see that the constant appeared in the as in multiplicative form. That means it multiplies the rest of the quantity. Okay. Any questions so far? Now, why don't we also say what it means to solve an initial value problem? And let me stick to this very, very simple differential equation that I have been working with this morning. So let me stick to y prime is equal to 3y. And what would constitute an initial value problem? We would have an initial value problem if, for example, I had asked that the solution that you find is actually equal at 0 equal to 5. Okay, so this would have been an initial value problem. So this is an initial value problem. And how do you solve this initial value problem? The general solution is known to be y is equal to c e to the 3x. So if we set y of 0, that will give us c on the one hand. And on the other hand, we want this y of 0 to also be 5. So that implies that c has to be 5. And the solution, hence, the solution of the initial value problem is y is equal to 5e to the 3x. Okay, so in other words, in most cases that we're going to discuss here, in the vast majority of cases, and I say this because you may have some rare cases in which this is actually not true. we're not going to really, I mean, we will encounter some such cases, but in the majority of cases, it will be just a little trivial step to find the special solution for the initial value problem. Okay, but you will see that I don't want to trivialize it completely and tell you that it's going to be just a nuisance to move from the general solution to the solution of the initial value problem. There will be at least one situation in this course where it's going to be an interesting task. It's going to be a little different when we actually have an initial value problem. In fact, as you're going to see, it's going to be important that we do have an initial value problem. Okay? Any questions so far?
Yeah, so I have some questions. So I'm just curious where you got the general solution from. Is that like, are we supposed to know how to solve that by now, or?
Absolutely not. We haven't solved a single equation yet. So I just told you that if you like, believe me that this is the general solution of this equation.
Okay.
Okay. For the moment being, the only thing you can do, and you can do that, is actually verify that what I gave you is a solution of this equation. That you can do. How? By just plugging in. If you plug in e to the 3x, then you can easily see that the derivative of e to the 3x is 3 times e to the 3x, which is 3 times the function itself. So that you can actually verify. Okay, but for the moment being, you don't have a clue about how to solve this equation. I promise you that on Friday, you will indeed know how to solve this very simple equation. Okay? You said you had questions, plural, so what's your next question?
Well, I mean, that would have been built on the fact that I didn't understand how to get to that part. So, but since we are not supposed to know how to do it.
No, you're not supposed to know how to do this. Okay. Any more questions, please? And let me remind you that this is the best thing. So please try to ask your questions exactly when they occur. Okay. You'll be doing everybody a favor. The question that was just asked was a very important question. I think many other people were wondering the same thing. So you're always doing many of your classmates a favor by asking such questions. Okay, here's what I want you, there's a situation, and this comes from the way that we solve some differential equations. So one of the things that you will realize as we proceed in our course is that this course is rich with a variety of ideas. I mean, you might have said, okay, we have seen integration, indefinite integration, and we have seen that you have integration by substitution, by parts, and then you have special methods, partial fraction decomposition, and trigonometric substitutions or special substitutions, induction, recurrence, reduction formulas, and so on and so forth. So there is a variety of methods. But the truth is that in the case of differential equations, the set of things that we're going to see is even richer and more diverse. So we're going to encounter really a vast variety of methods that allow us in very agreeable cases, as we're going to discuss later, to solve differential equations. So in some of those cases, you get a solution where it's not immediately clear, and in some cases it's not even important that you can solve for the dependent variable. In this case, for example, for y. Okay, what do I mean by this? In Calc 1, you have seen that a function can be given explicitly or implicitly. Okay, what does it mean to give a function implicitly? Giving a function implicitly simply means, and let me just give you one that you cannot really solve so easily. It can be solved, but not so easily, and I don't think. So imagine that you have the following situation. So somebody tells you that y is a function of x by means of this formula. And of course, what each one of us would like to do in this case is actually solve for y. But like I told you, even though it's not impossible to solve for y, it's very hard. And if you want me to make it impossible, I could replace the exponents by 5, and then there goes your possibility of actually solving for them. So in this case, you cannot even hope to solve for y. But what this means is that if somebody gives you a value of x, then you can use any means available to you, possibly numerical methods, and find what y is. And this, of course, gives you a genuine relation between input and output. So you still have a function. It's just that the function is not given explicitly. Okay, it's defined implicitly. And that's a possibility. What I want you to understand, as I said a moment ago, is that there are methods of solving differential equations which by their very nature are going to give you such implicit solutions. And I would like to give you a very simple example. So imagine that somebody gave you the following differential equation, y plus 2x plus xy prime plus 3y squared y prime plus sine x is equal to 0. Okay, I'm sorry, this is supposed to be a y prime. So imagine that you had this situation right here, okay? And you want to solve this differential equation. And somebody tells you that the solution of this equation, or I should say here, a solution of this equation, is given by, and here's your function, x squared plus xy plus y cubed is equal to cosine x. Okay, and somebody tells you, here's the solution. And now you scratch your head and you say, well, how in the world am I going to verify that this is indeed the solution of this equation? I mean, in the case that we studied before, in this case, when we were given the solution, either the special or the general, they were solved for y. We could find their derivatives, we could plug into our equation, and we could check the validity of that solution. Here, how in the world are we going to do this? This is not going to be an important part of our discussion or any particular concern of ours, but I would like you to know how in some cases, in some simple cases like this, you can actually check that a given implicit function is a solution of a certain differential equation. And the answer is, you will need to use implicit differentiation. Do you remember how to do implicit differentiation? Pretty much the idea is as follows. When you do implicit differentiation, you just assume that x is your dependent variable and y is your independent variable. Occasionally, you can actually, you may have, this choice may be left up to you, but this is how we're going to consider it right now. And if you use implicit differentiation for the suggested solution, again, let me emphasize this, never mind how this solution was found. If you do implicit differentiation, you will see that you get 2x, then you need to apply the product rule for xy, and this means that you have the derivative of x, which is 1 times y, plus x times the derivative of y, which is y prime. And now what do you do about y cubed? Its derivative by the chain rule, I mean, the chain rule tells you just take the derivative as you would normally have done, meaning 3y squared. Okay, but then it tells you follow it up by the derivative of the function of the inner function. So in this case, it's y prime. And of course, this would be negative sine x. So you multiply, you differentiate both sides. And when you do so, you realize that pretty much the equation that we have got here is equivalent. It's pretty much the same as the equation that we have up there. Okay, and this is just a simple-minded way of checking that an implicit solution is really satisfies, or an implicit function, an implicitly defined function really satisfies a given equation. Again, this is not going to be something very important, but I want you to know how you can do this in simple cases like the one that we just saw. Are there any questions, please? Yeah, so the question is, where did I get this y right here? And pretty much the answer is that all of this thing was obtained by differentiating xy and using the product rule. Okay, so by using the product rule. Yeah. Any more questions, please? Okay, great. So now here comes the important question, and we need to ask such questions. And as I'm going to say, these questions are not even to be taken for granted in very general setups. So we embark in a journey where we will try to solve all sorts of differential equations. Sometimes because they're interesting, but mostly because they're encountered in interesting applications. And we're going to see where and how that happens. So the question is, what gives us any kind of hope that these equations do have a solution? And again, I would like to bring this in parallel to the case of indefinite integration. That's always something, I mean, remember, always consider from this point forward, indefinite integration as a special case of solving differential equations. So many times you can ask what it is that we know in the case of indefinite integrals that might be useful in the case of differential equations. And in the case of indefinite integrals, from the very beginning, you were given that with under very mild conditions, a function has an antiderivative, which means that it makes sense to try to find an antiderivative. It's not like you're trying to find something that doesn't exist. In fact, let me remind you that the first form of the fundamental theorem of calculus was saying that if you have a function f which is continuous, then you can literally write its antiderivative as the definite integral from a to your generic point x of f of t dt. This doesn't really help you to find the antiderivative itself. It's pretty much like chasing your tail. I mean, it doesn't do much for you. But theoretically speaking, it tells you that antiderivatives do exist. And we wish to have a similar result here. Now, of course, the result here is going to be a little more convoluted. Before I give you the result, I just wanted to address one question that was asked in the chat. So will all solutions be a solution for homework and tests? What exactly do you mean by that? Or group of solutions? Usually, it will be clear whether you're being asked to find the general solution or the solution of an initial value problem. This will be the two setups that you will have. Okay, so you will either be asking, either be asked to find the solution of an initial value problem, which would be a specific function, or otherwise the general solution of a differential equation. And I would like to emphasize that in this second case that you're looking for the general solution of a differential equation, you will usually have the kind of situation that we just described. So it's not like you're going to have two solutions that look very much different from each other. Okay? Okay, I hope I covered what you were wondering about, but please, by all means, let me know if I can do a better job. So, so yeah, let's talk a little about the existence theory, and it's a very nice theorem, and it's directly related to what we're going to do in the second half of our class today. It's usually referred to as the Picard or Picard-Lindelöf. These are two very famous mathematicians. So Picard-Lindelöf existence theory. So our starting point here is a differential equation that looks like this. Y prime, so given the differential equation y prime is equal to f of xy, and an initial condition y of x naught is equal to y naught under Mal conditions that I'm going to discuss. Obviously, for this reason, I shouldn't tell you that this is the precise form of the theorem, but you will see what I mean by that. Under Mal conditions, there is an interval, an open interval, I containing x naught, and the function y of x defined on I, such that y prime of x is equal to f of x comma y of x. In other words, this function y is a solution of the differential equation. That's what we're saying here. That's what we're saying here, that you can solve this differential equation. And I would like to discuss a little what the Mal conditions are. So I could have made this part of the theorem, but let's discuss what they are. And the best way to discuss what they are is to look at the point through which that particular solution is supposedly going, meaning that's the point x naught, y naught. So this point x naught, y naught, imagine that it's a point somewhere here on the plane. Let's say that this is the point x naught, y naught. Okay. Then here's what we mean by mild conditions in this particular case. There is a rectangle containing this point over which this function, the function f of xy, is defined. It is continuous. And, you know, here, the condition that I'm going to give you is sort of not as general as it can be, but it will be good enough for us. Its partial derivative with respect to y is continuous. This condition can be made much milder, but you know, this will be good enough for us. And such conditions are automatically satisfied for any equation that you're going to encounter in this course. Such conditions are automatically satisfied. Basically, when those conditions are satisfied, what we're saying is that around the point at which the initial value problem is centered, which is the point x naught, right? You can find a small interval and the function so this will be the function y of x, the supposed solution of the problem that goes through that point. Okay, that's pretty much what we're saying here. Yeah. And satisfies the differential equation. And there are several things to discuss here. So there are many things actually to discuss here, and that's why I would like to pause and let me ask you if you have any questions so far on this raw statement of the theorem that I gave you. Okay, again, this theorem, let me emphasize this. This is not a theorem that we're going to apply directly in any conceivable situation. However, what this theorem says, and it's important for what we're doing in this course, what this theorem says is that solutions do exist, which means that our task of trying to find those solutions is really a meaningful one. We're not trying to find things that do not exist. So these things, the solutions of a differential equation that has a reasonably good form, do exist. And so it makes sense for us to try to find those solutions. Okay, so questions, please.
What do you mean by under mild condition? This is
the
different other conditions we could consider?
No, the mild conditions that I said are these ones that I described here. So the function f of xy is defined in a nice way over a rectangle, and its partial derivative with respect to y is continuous. These are precisely the conditions that I want in order to ensure that a solution does exist.
Thank you.
Okay. Any more questions, please? So in other words, let me elaborate a little more. It doesn't mean that if you give me any crazy function f, a function of two variables, and you make up some crazy differential equation, that there has to be a solution. Okay, but under these conditions, there will be a solution. And one thing that I should add to it is that this solution is guaranteed to also be unique. Okay, so under these conditions, so this solution is unique. Okay, so if somebody else comes up with a different solution, at least over an interval surrounding x naught, there will be a coincidence between the two solutions. Okay. And this is something that is used all the time, pretty much. As I said before, this theorem is not going to be used in any explicit form in our work. It's just the underlying theoretical background that tells us that what we're trying to do is meaningful. Because just imagine the opposite situation, the situation in which you're trying to solve an equation and you don't even know whether a solution should exist or not. Okay, the truth is that for many of the methods that we're going to explain, this is besides the point, because part of the method is showing that the solution exists, but in many other cases, it's of fundamental importance to be assured that this solution does indeed exist. Now, there is another interesting part to this whole discussion that was initiated. And the interesting part is this. So first of all, there are a couple of things to discuss here as to how general this statement is. So take a look at the kind of equation that I told you that we have here. It's y prime is equal to f of xy. What can you tell me about how generic this differential equation is? So what are some things that stick out regarding how general this equation could be considered? One-to-one. Well, the number one is actually very important here because it's a differential equation that has to do with the first derivative. And we said that differential equations could have to do with the second derivative, the third derivative. So this is a first order differential equation. So at first glance, sure. So at first glance, it seems that this differential equation is just, or this theorem is restricted on differential equations of the first order. Okay, so there is a trick that can make this theorem work for higher degree differential equations by replacing the equation itself with a system of equations, and then you will need a sort of matrix of equations to pretty much describe this, and the proof of this theorem applies. So that's the first thing to note here, that even though seemingly this result works for first order equations, it can be made to include higher order equations. Okay, something that you don't explicitly see right away, but as I told you, this is going to be a possibility. Okay, so that's the first thing to keep in mind. The second thing to keep in mind is even if you restrict your attention to differential equations of the first order, who says that you can solve for y prime? I mean, here you can see that this equation comes solved for the derivative. In other words, what I'm saying here is that if you go back to the two equations that we have seen today, this equation is fine because you can see that y prime is expressed in terms of x and y. You don't see x, but that doesn't matter. But then you have this equation right here, the second one that I gave you, this one, where it's not an impossibility to solve for y prime, but at least your equation doesn't come as solved for y prime. Again, let me emphasize here that it is possible, this particular equation, to solve it easily for y prime, right? You can isolate y prime easily. But what if somebody gave you an equation where it seems to be impossible to solve for y prime? Again, my favorite examples here run on things like this. Something like this. Take such an equation. Okay, and good luck isolating y prime here. So is the theorem that we just gave useless for such an equation because it's not solved for y prime? And the answer is that there is a theory in calculus of several variables that sometimes we mention in passing. I did mention it last semester, but regrettably, we don't pay too much attention to it, even though it's one of the most important theorems of that particular theory, that says that, again, under mild conditions, usually those mild conditions have to do with some non-vanishing of a partial derivative or so. And in other cases, it can be a condition that comes from linear algebra. But regardless, under mild conditions, you can always, I'm sorry, under mild conditions, you can solve for y prime. Theoretically. There are more things that can be done theoretically than things that can be done explicitly algebraically. And I want you to understand this. I want you to understand this, that the relations that exist theoretically far surpass the relations that exist algebraically. And to give you an idea about what I mean, let me put it this way. Allow me to open a parenthesis, and then I'll give you a short break so that we can catch our breath and then look at Euler's method. But basically, what I'm saying is the following thing. Consider the following algebraic equation. X squared plus x minus 1 is equal to 0. This is a very famous equation, right? The golden ratio is pretty much its solution. And it looks like what? It's minus 1 plus or minus square root of 5 divided by 2. So you can solve this equation, right? And you can write down the number explicitly. Okay, and now consider this equation. Make the 2 into a 5. And you can show, I promise you, you can show that this equation, the same equation, this similar equation does have a solution. It is a very interesting and comparatively deep fact that you cannot express the solution of this equation in any form comparable to what you had in the case of the second degree. Okay, so in other words, the solution exists. It's an algebraic number, as we call it, but you cannot visualize it using radicals. And it is our human intuition that pushes us to visualize things using radicals. And basically what I'm telling you is that in this situation, that's impossible. Here's another example. Take the antiderivative of the function e to the x squared. Okay, again, the fundamental theorem of calculus tells us that this antiderivative exists. What is it? Good luck finding it. I would tell you, don't try to find it. Why? Because it's not a function that can be expressed using the functions that we have seen in our mathematical career so far. Okay, which means that if you very badly want to use that function, you have to give it a new name. So this tells you that as far as numbers are concerned, as far as functions are concerned, we have not named everything that exists out there, which means that if we ever run into a situation that we need to use them, we can simply not call them anything. We have an inability to express them directly. And that's what I want you to understand is the case in what I was discussing here, that you have this differential equation and you ask yourself, can the existence of a solution of this equation be justified by the theorem that I just gave you? And you might think to yourselves, well, if you are to apply this theorem, you should be able to isolate y prime. And basically what I'm telling you is that theoretically speaking, y prime can be isolated. But in concrete terms, this is impossible to do. Okay, theoretically it can be isolated, but we have not named all functions that exist out there, and that makes it an impossibility for the particular case. And please understand that this is something that we're going to encounter time and again. Okay, so this is something that we're going to see over and over that indeed, in many cases, there are things that are going to solve it. There are solutions, there are functions, there are numbers that if we were able to express them directly, we would have a concrete form of some solution that we're seeking, but it's practically impossible to do so. It's only theoretically possible to say that they exist and they can be identified. Okay, this is a theme that I'm going to discuss again later because I want you to digest it, and this is where the theoretical challenges are being met by numerical methods that allow us to find approximations. Meaning, in the case that I mentioned before, maybe you cannot express the solution of this equation in any form that you would like if you want to see radicals, but you can find as many decimals as you like to that solution. Same thing with this function. Maybe you cannot find what this function is as a nice formula comparable to when you solve other types of integrals, but you can actually have a very nice, theoretically, a very nice function that for which you can compute to any degree of approximation its values for any particular point. Okay. Questions, please. Okay, so why don't we take a 5-minute break and then we're going to discuss Euler's method when we come back. Okay.
Oh, Professor, I think you're muted.
Yes, I'm sorry. Thank you so much. So let me start over what I was saying. So I was saying that we're going to look at Euler's method. And for that reason, we're going to have a differential equation with an initial value problem. And I would like to look at what this differential equation, what this initial value problem really means from a geometric point of view. And you will see that by doing so, we will be able to actually understand very well how Euler's method works. However, before I started saying all these things, I had asked if there were any questions from what we did before. So let me pause what I'm doing right now and re-ask that question. Are there any questions on what we did in the first part of today's lecture? Okay then. So let's see how we can draw this, sort of speak. So it says that y of 0 is 1, which means that whatever function would be the solution to this differential equation, it would go through the point 0, 1. Okay, do we all understand this so far? But I don't know how you draw this function. So, one of you might draw it like this. Somebody else might draw it like this. In all cases, it should go through, oops, I destroyed everything. Let me start over. It should go through this point, the point 0, 1. Okay, so there are many functions that we can draw. But I claim that not only do we know that it will go through the point 0, 1, we have another very nice piece of information. But what is the other piece of information? Can anybody guess what the other piece of information is? Look at your differential.
We know the slope.
Exactly. Very good, everyone. Many of you answered that question. We know what the slope is going to be. And we know that the slope at 0 is going to be our x here, which is 0, plus the y, which is 1, which means that it's 1, which tells us already that if we were to try to guess what our function looks like, we know that it goes through the point 0, 1, and we know that it has slope 1. So it will go like this. Okay. So you could draw any curve that has this specific slope. That limits a lot the kind of curves that you can draw. So for example, it wouldn't make sense to draw some curve that is decreasing around that point. That wouldn't make any sense. Okay. Okay. So now Euler's idea is the following. You cannot certainly, you see how I drew a straight line. That could be the tangent to the solution at that point. So what Euler's, excuse me, what Euler's idea was, is that you can assume that for a very small interval, the solution is indeed the line. And here, allow me to do the following. Allow me to allow this curve to go for an interval of length 1. 1 is by no means a small number. Okay, so if I wanted a really small number, I could say 0.001, right? And I could do that if I had a computer with a computer program, let's say. But the point remains the same. Allow me to say that, you know what, let's let this function run as a linear function for an interval equal to 1. And let's ask ourselves, what is the new point that we're going to end up at? And the new point that we're going to end up at can be found by using the following. Since you have a linear function, and you know that the tangent to that linear function would look like y of x is equal to y of 0 plus the slope y prime at 0 times x minus 0. That's the equation of the tangent after all. You can, from here, you can say that y1 is the y of 0 that you had, which was 1, plus the slope, which we said 1, times the length of the interval, which is again 1. So this would be equal to 2. So you can argue that the value here is 2, which means that you have the new point 1, 2. And the idea now is simple. Keep doing this. Okay, keep doing this. Meaning what you did with 0, 1 before, keep doing it for 1, 2, and try to guess what the value will be at 2 now. Okay, let me give you 1 minute for you to try to do it yourselves, just by using your differential equation and the fact now, before you knew that y of 0 is 1. Now you can argue that y of 1 is 2. Okay, so try to use your differential equation. So y prime is equal to x plus y, and the fact that y of 1 is equal to 2, and try to figure out what the value of the function will be at 2 if you were to continue again with a line. Obviously, a different line now. Okay, give it a try. Okay, let's do it together now. So the first thing that you need to do is find what? The new slope, right? So you will have y prime of 1 is equal to the value, the x at 1, which is 1, plus the y at 1, which is equal to 2, right? So this will give you 3. And which means that now you have to continue from this point forward with slope 3. This is a much steeper slope, right? Which is going to take you where? So now y of 2 is going to be y at 1 plus the slope, which is 3. So if you like y prime at 1, if I want to write it in a theoretical way, times 2 minus 1. Which of course will be equal to 1 plus 3, which is 4. So I will end up at the point 4. So this will be the point 24. So if somebody asked me, if you are to apply this idea by Euler in a just by taking 2 steps. So by starting with the initial value problem, y prime is equal to x plus y, and y of 0 is equal to 1, and using Euler's method, in 2 steps, we can guess that y of 2 is equal to 4. Okay, and I want you to understand that this is very crude, right? Because you take a lot of liberties here. You assume that your solution is linear, is a line, has a graph which is a line for a pretty long interval. Okay, that's not something that you can so easily assume without expecting to have a pretty big error. So can anybody tell me, if you conceivably had many more resources, computational resources, what would you do that would make this approximation much better? Can anybody tell me, if we wanted to make what we just did, let's say that our goal was to guess what the value is at 2. For whatever reason, we wanted to know what the value of the solution is at 2. How could I have done what I just did in a much more precise way that would have given me a much more precise idea about what to expect. Exactly. You would do it in a lot more steps. So to give you an idea, you would use 100 steps, not 2 steps. So you would subdivide the interval from 0 to 2 into 100 pieces. So each one would have length 0.02. And you would repeat this 100 times, and that would have given you a much better approximation of what to expect at that particular point. Okay, and then if you were not happy with that, you could have done it 200 times or 1,000 times. And therein lies the idea behind the proof of Picard's theorem. So what Picard's theorem, if you go through the proof of that theorem, you will realize that one builds an approximate solution using Euler's idea, using Euler's method, and eventually shows that as the number of steps tends to infinity, what you actually get is the real solution. It's a really beautiful theorem. It has a really beautiful proof. It's a pity that we cannot go over this proof, but the proof of this theorem is really Euler's method. And that's the amazing thing that we have here. Okay. Any questions so far?
Professor, I believe I understand Euler's method, but in your green writing on the screen, the first line says y of 1. And when you plugged in numbers for that, you have 1 plus 3. But wouldn't y of 1 be 2?
Y of 1 goes 2. You're absolutely right. And this is a mistake. So thank you for catching this. So this has to be 2 plus 3. I would have liked to tell you that I did it so that I can see if you were following, but the truth is that this was a mistake. So, and this should be 5. Thank you so much.
Okay, thank you.
Okay. And then I just want to be sure. So the equation you showed us at the top, like above the line, which is y of x is equal to y of 0 plus y prime of 0 times x minus 0. So is that Euler's method? That's the part that's Euler's?
That's really the equation of the tangent. And Euler's method is based on that equation. Okay?
Okay.
So here's what we're going to do now. This is the idea behind Euler's method. Now we're going to make it much more formal. We're going to formalize. Okay, so that we can do it in a much simpler way. So here's the idea. Here's how we're going to do things. So somebody's going to give us a differential equation. Y prime is equal to f of xy. And an initial value problem that comes with this equation. So y of x naught is equal to y naught. And we're going to be given a number of steps and a step. So h will be the step. In the previous example, the step on the x-axis was equal to 1. So we were proceeding in steps horizontally in steps of length 1. And we will want to ask, what is the approximation for y of x naught plus nh? So we want to take n steps. Okay, so the idea, and let's call, to make it easier for us, let's call x naught plus nh, let's call this xn. And let's call the value of the function at xn, let's call it yn. And finally, the derivative at xn, let's call it yn prime. Okay, so let's use this notation. Okay, so I'm going to build a table where I'm going to have xn, yn, and yn prime. So on our very first step, so for on a very first step, so for n equals 1, for n equals 0, we simply have x naught, y naught, and then when you compute the step, it's going to be f of x naught, y naught. And then the next step will be x naught plus h. And the important thing is what y naught is going to be. I'm sorry, what y1 will be. And y1 will be y naught plus y naught prime times the step h. So in other words, our usual relation will be that ym plus 1 is going to be ym plus ym prime times h. This is the only relation that you need to know. Meaning, if you want to find the value of the function at the next step, you have to take the present step and add to it the derivative times the length of the step. Let's do an example. Let's do an example using this terminology. So, use Euler's method to approximate y of 3 in 3 steps for the initial value problem y prime is equal to x minus 2y for y of 0 is equal to 1. Okay, let's do this. So we will have xn, yn, and yn prime. These are the things that we want to compute. And let's start with the very first ones. So x naught is 0, y naught is 1. And what is y naught prime? So what is y naught prime or y prime at 0? To find y prime at 0, you need to plug in x minus 2y. So it's going to be 0 minus 2 times 1, which is negative 2. Okay, let me pause here and see if you have any questions. So do you all understand how we got x naught, y naught, and y naught 0? Y naught prime, sorry. So this is, if you like, for n equals 0. Any questions here, please? So to find for n equals 1, the crucial step is to realize this, that y1 is going to be y naught plus y naught prime times the step. Okay, this is the relation that we're going to use over and over. So what is this equal to? Y naught is equal to 1. The derivative goes negative 2, and the step is equal to 1. So this will be negative 1. Okay? So this means that this is 1, this is negative 1. And now again, the crucial step will be to find what the derivative is at y1 prime. It will simply be x1 minus 2y1. Where? From the differential equation. So that is going to be 1 minus 2 times negative 1, which is 3. So this will be 3. Questions, please. Okay, one more step, n equals 2. So we will have xn here is 2. yn, y2 will be what? y1 plus y1 prime times h, which in our case is y1 we said was -1, plus 3 times step, which will give you 2. So this is 2. And how much is y2 prime? y2 prime will be x2 minus 2y2, which is the same thing as 2 minus 2 times 2, which is -2. So this will be -2. And I will take my last step. And are there any questions before I take my last step? So here it's the third step. Xn will be 3. The initial condition, let's count it as the 0th step, okay? And I think it is clear from the fact that I'll try, when I give you a problem like this, to always make it as obvious as possible where I want to end up with that. Yeah. So y3 is going to be y2 plus y2 prime times h, which is the same thing as 2 plus -2 times 1, which is 0. And that's it. Okay, you don't need to find y3 prime because you were just looking for this. So y3 is approximately equal to 0. That's our final answer. Okay. So this is the kind of standard problem that you should expect. That's the kind of problem that will be our first quiz on Friday. We will take our first quiz on Friday, and it will be very, very similar to this. Okay. I would like to do one more thing before finishing, but I would like to also take the attendance. So at this point, please send me as your keyword the word Euler, the name of the mathematician whose method we're learning today. So please type Euler in the chat for everyone. Send it to everyone. This way I can check it from the recording.
Professor, I have a quick question.
Mm-hmm.
I just want to make sure, like, so when it comes to H for these problems, will it tend to stay constant, or will we get maybe like, will a different problem, will the H be changing?
This is an excellent question. Typically, H remains the same. So you have the same step.
Okay, thank you.
Theoretically speaking, you could be changing your H every single time. Nothing prevents you from doing a step of length 1/2 in the beginning, and then taking a step of length 1/3, and then a step, but we never do it. Okay. And
okay.
I should not say never, but in this course, you will not see anything like that. Okay.
Okay, thank you.
That's an excellent question. Yeah, and right. So in this case, just to make sure that we all mean the same thing, this number for the duration of this problem is going to be considered constant. And exactly because I told you to go from 0 to 3 in this step, in 3 steps, H is equal to 1. Okay, so you will be asking yourselves, if I want to go from 0 to 3, if I had told you 6 steps, then H would have been 1/2. Okay? And here's one interesting thing I would like to end the lecture with. There's a very interesting situation in which we can take an indefinite amount of steps. And then, so consider the following problem. Y prime is equal to y. and y of 0 is equal to 1. And approximate y of 1 using Euler's method in n steps. So now I doubt that you will see something like this or on a quiz or an exam, but it's a very interesting problem. I think I do have something like this on the homework, but here's what the situation is. Excuse me. So here's what the situation is. What would I do here? The idea is still the same. So I should have my y, let me not call it n now because I already told you n steps here. So let's call this xk, yk prime. Okay, so I start with 0, right? And I know that y of 0 is 1. And now what is y prime? So y prime is going to be equal to y, which is 1, right? Okay. Then I want to go to my next step. Since I want to go from 0 to 1 in n steps, h will have to be 1 over n, right? So here I will have 1 over n. And now you have to ask yourselves, what is y1? So y1 is going to be y naught plus 1 times the step, which is 1 over n. So this is really 1 plus 1 over n. So this is 1 plus 1 over n. And what is y prime at 1? It's also 1 plus 1 over n. Why? Because it's equal to 1. Let's take one more step. So here I'm at 2 over n. And what is y2? y2 will be y1 plus y1 prime times the step, which is h, which is y1 is 1 plus 1 over n, plus y1 prime is 1 plus 1 over n, times the step, which is 1 over n. And this, you can think of it as this times 1 plus the same thing times 1 over n, which gives you 1 plus 1 over n squared. So this will be 1 plus 1 over n squared. And this will give you the same derivative. And if you take one more step, you will realize that you will find 1 plus 1 over n to the 3rd power. And here you will get the same thing, which means that eventually when you reach the nth step, which is 1, since each time you get, it gets multiplied by 1 plus 1 over n, you're going to get 1 plus 1 over n to the n. So the y of 1 is approximately equal to 1 plus 1 over n to the n. Does anybody remember what we get if we let n tend to infinity? Does anybody remember what happens as n tends to infinity? One plus 1 over n tends where? What is the limit of 1 plus 1 over n to the n? No, it's not 1. It's a good guess, actually. It's an excellent guess. The problem, the reason why it's not 1 is the basis tends to 1. Yes, but the exponent tends to infinity. No, it's not 0. It will be at least 1. And it's not infinity, actually. Infinity is an excellent guess, but it's not infinity. It's the number e. Okay, I may want to come back to this in the next lecture and explain it a little more. And indeed, if you think about it, the solution to this differential equation is none other than y is equal to e to the x. And e to the first power is e, which is exactly what we're reaching by applying this method an indefinite amount of times. Okay, this is an excellent example. Now, your homework for next time has already been posted, and it's due Friday night. I remind you that this is due, that tonight you have your optional homework. And what I would like to say, and this is the reason why I would like to come back to this example for a little bit on Friday, is that problem number 3 of your homework is very, very similar to this. So problem number 1 is just a show that something is a solution. And problem number 2 is the traditional Euler's method, what we did a moment ago. And problem number 3 looks very much like this last example that we did here. This last example that we did is just for the sake of the homework. And what you should expect to see as your quiz on Friday is something similar to what we did before, this example right here. Okay, I will post the recording when it becomes available. Please do what we said before. Work out these examples many, many times before you try the homework. Okay? Thank you for this question, Jenny. No, unfortunately, the answer is no. You may not use a calculator for any exams or quizzes, but I promise you that the problems are going to be given in such a way that no calculator will be really needed. Okay? All right. Thank you, everyone. Have a great rest of your day. I remind you that I have office hours at 11:50 at the same link in case you would like to ask more questions. Bye.